Thank you. Thanks very much. So this is joint work with Ryan Shifler, and we put the paper on the archive recently. So if you want to take a look, yeah, there's more detail there. So I'd like to start by explaining a little bit what curve neighborhoods are. So they were introduced by Buch, Chaput, Mihalcea and Perrin in 2013 with the aim of studying quantum K-theory for communiscule homogeneous spaces, and more specifically to prove finiteness. And there are several ways to define it. Maybe the simplest one that I'm going to start with is that if I take X, my homogeneous space, then, well, it's not going to always be homogeneous, but let's start with that. And I take a subvariety V, I fix myself a degree, then I'm going to consider the closure of the union of degree irrational curve through V. And this is the curve neighborhood. And in what I'm going to do, we are going to look at, so our subvarieties are going to be Schubert varieties of these slightly unusual spaces, which are odd symplectic Grassmannians. So there are several uses for curve neighborhoods. One of them, as I said, is quantum K-theory. And you can also say things about the, well, this is related, but you can also say things about the quantum cohomology. In particular, we haven't done this here, but that's something that could be potentially be done, is to look at minimal degrees in quantum cohomology. So that's something where curve neighborhoods can be useful. Okay, so next, I'd like to explain the second part of the title. So what are odd symplectic Grassmannians? So it's a slightly strange term because symplectic Grassmannians, first of all, what would they be? So I would take an even dimensional vector space, and I would take a symplectic form on that vector space, and then I would fix myself some integer k, so and I would look at all the k-dimensional vector subspaces of my even dimensional vector space, which are isotropic for the symplectic form. And this is a homogeneous space in type C. It's quite well understood. But what I'm doing here is a little bit different. As I said here, I'm looking this time at an odd dimensional vector space. And I'm still going to look at an antisymmetric form, but this time I can no longer assume that this is going to be non-degenerate, but I can make sure that the kernel is as small as possible. So I'm taking that the kernel of the form, I'm taking it to have dimension 1. And such an object, such an omega, we call it an odd symplectic form. And as I was mentioning, for symplectic Grassmannians, we're going to fix some integer k, which will be the fixed dimension of our spaces. And so my object of interest for that talk is IGKE, so which I will generally call X later on. And this is the set of all subspaces, so vector subspaces of E, so of my C to the 2n plus 1, which are k-dimensional and are isotropic for omega. So our odd symplectic form. So it turns out that it doesn't matter which omega I have chosen. So actually in the notation later on, I will not use E, but I will merely encode the dimension of E to n plus 1. Right, here I've taken one, so k between, oh yeah, I could have taken technically k between 1 and n plus 1. Actually, the cases that have non-homogeneous behavior that are not homogeneous, they correspond to k between 2 and n. So if I take k equals 1, well, I look at one-dimensional subspaces and I ask that they are isotropic for an antisymmetric form. Well, that's all of them. So this is just projective space. So I'm not going to focus very much on that case. And similarly, if I take k equals n plus 1, then I can I notice that all of my spaces V will contain the kernel. That's the only way that they can be so large. So then I can mod out by that kernel and I get a variety that's isomorphic to a Lagrangian Grassmannian, so he is homogeneous. So, okay. Just a long-winded way to say that, well, actually here I could have taken 2. This is really the case where I'm going to have my special behavior. So these spaces have been studied quite a lot. So Mihai is probably the first one, as far as I know, who studied their properties, also studying odd symplectic flags. Then Pasquier looked at some varieties called horospherical varieties. I'm going to mention that a little bit later. And these are examples of horospherical varieties. Yeah, and then there are some results by myself with other people and by my collaborator with other people as well. And I'll probably tell a little bit more about this later. Right. One thing already that I'd like to say about the structure of those spaces. So I said in the beginning here that these are quasi-homogeneous spaces, so I'll clarify that later, and with homogeneous-like behavior. And I'd like to give you some sort of an idea why we have this behavior similar to that of homogeneous spaces. And this is because I can embed my odd-dimensional vector space, which I use to define odd symplectic Grassmannian, into a larger even-dimensional vector space, and my odd symplectic form omega, I can extend it, well, non-uniquely, but I can extend it to a symplectic form on this larger space. And also, if I take a complement of the kernel, then I get a smaller even-dimensional space, and I have these nice little embeddings here. So my odd symplectic Grassmannian is sandwiched in between 2 homogeneous spaces, and they will both play a role. So the first one, this IGK-1 F, we will see that it will give us, it will give us one of the orbits for one of the actions we're going to look at, and then this one we'll see that the odd symplectic Grassmannian actually is a Schubert variety of this X even. Okay? Right. So now I'd like to talk a little bit more about the group actions I'm considering to say, try and say, well, why is it quasi-homogeneous? And there are 2 main actions. The first one is the action of the automorphism group, so which is called the odd symplectic group. This odd symplectic group is defined in a very analogous way to the symplectic group. So this is just the group of matrices, so or linear maps on my space E that preserve the odd symplectic form. It's an algebraic group, but one thing to notice is that it's non-reductive. And it was extensively studied by Proctor in 1988. Of course, yeah, there's lots of results about it that I will not mention in a lot of detail. But under this, the action of this group, I have 2 orbits. One is isomorphic, as before, to this. So I mentioned in a slide before, this IGK-1F. So this corresponds to the closed orbit. And then you have the complement, the open orbit. So that's what I mean by quasi-homogeneous, is that I have yeah, an open orbit for the action of the group. And actually, I have in that case only 2 orbits, so that's as close to homogeneous as it can be in a way. The other group that will be of interest is simply just the symplectic group. And this is, so I mentioned that Pasquier had studied a family of varieties called horospherical varieties in his thesis and in this paper. This group is just the symplectic group, yeah, the sp2n. And for this, I have more orbits. So I have 3 orbits. I still have the Z, but I have an extra one, which is consists of all the subspaces that are contained in my complement of the kernel here. And this is just, yeah, this is, so you have these 2 closed orbits which are homogeneous, and then you have the complement. And well, it turns out that this complement, the open orbit for that action, is a C star of K bundle over a homogeneous space, and that's part of, well, that's part of the definition of being horospherical, if you want. Right, and it turns out that to study the Kerr neighborhoods, both of these actions are useful, and I'll try to demonstrate why in the talk. Right, so I'd like to start by stating the main result. There's a lot of notation that we cannot really understand at that moment, but just to keep in mind our objective. So the first thing is that we'll see later that my X, so my out-symplectic Grassmannian, has a Schubert decomposition because it is a Schubert variety of an even symplectic Grassmannian. So I can define Schubert varieties in there. And our result, so with Ryan, is that we will describe the curved neighborhood of the Schubert varieties. So I will have some indexing sets that I will explain for the Schubert varieties. And then X lambda, for lambda an element in this indexing set, will be a Schubert variety. I'll fix myself a degree as well. So remember, I want to look at all the points that are connected to a point in the Schubert variety by a degree D curve. And I have 3 cases. So the first case is if my Schubert variety intersects the open orbit. In that case, I have just one, so my curved neighborhood will consist of just one one Schubert variety. And then if I take a Schubert variety of the closed orbit, I have 2 possibilities. So it could be that I have 2 components, or I have 1. So for D equals 1, this was already established by Ryan Shifler and Leonardo Mihalcea. And yeah, so here we're going to explain how we can describe this also in a very explicit way. So a little bit more about the indexing sets. There are 2, well, there are more than 2 possible ones, but I'll focus on 2. So one is the Buch partitions, so strict partitions or K-strict partitions, and other partitions that were introduced in a paper of Shifler and Withrow for type BC, I think. And they're called BC partition, not because of the type, but because they are compatible with the Breuer order. So BC stands for Breuer compatible. And I'll explain all of these later. And also I'd like to mention in the case where I have just one component, this component, so for the curved neighborhood, this component always intersects the open orbit non-trivially. However, in the case where I have 2, which is here, I can I have one intersecting the open orbit and one that's entirely contained in the closed orbit. So, right. So it's an interesting difference from the homogeneous case. For homogeneous spaces, curved neighborhoods are always irreducible. And here we see that's not the case. Okay. So, right. So my objective for this talk is to explain the result we got. So how we got this description, and also explicitly what are those indexing sets and how I can really concretely. So it's not just a result about, oh, sometimes you have one irreducible component, sometimes you have two. This is also concrete. If you give me a Schubert variety, I can describe really explicitly what are the two components. All right, so these indexing sets. First thing to say is that it's a result of Mihai that the out-symplectic Grassmannian is a smooth Schubert variety of this even, this symplectic Grassmannian. And that means that it inherits the whole, it inherits a Schubert decomposition. And so, well, whatever indexing set I have for Schubert varieties in symplectic Grassmannians, I can have a subset of this, which is going to index my Schubert varieties for out-symplectic Grassmannians. And the best known one, I would say, apart from, well, the Weil group, would be those Buch and Tambakis partitions. So let me just, we're not going to, in this talk, I'm going to focus more on the other set because it's less, maybe less familiar. But I'd like still to explain what those are. So if I'm in the symplectic Grassmannians, then I can look at partitions whose Young diagram is contained in a k times 2n plus 2 minus k rectangle. And the condition is that being n plus 1 minus k strict. That means that if I have a part in my partition that's larger than this n plus 1 minus k, then it needs to be larger than the next part in the partition. And so such partitions form an index set for Schubert varieties of the symplectic Grassmannian. And now there are different ways to translate that into an indexing set for the out-symplectic Grassmannians. But what we do here is that we just take we define a subset. I haven't explained here how you define it. A subset, and then we just remove one box from each part of the partition. The reason I do that is that this k is the codimension, and so I do this shift so that actually the codimension of the Schubert variety is indicated by the number of boxes in the partition. So that's the one big advantage of these partitions, is that if I have a partition here, then I can easily read the codimension of the variety just by counting the number of boxes in my partition. However, there's a drawback, which doesn't matter always, but matters for what we're doing here, which is that I cannot read inclusion of Schubert variety by looking at the inclusion of partitions. So, and this is something that the second indexing set is designed to remedy. So, okay, let's go. And the second indexing set, so these are these BC partition, and it takes a little bit more explaining to define it, but the idea is similar. So first of all, I'm going to define them in the case of the symplectic Grassmannian. So as in the BKT case, I look at a partition mu, which has k part, and the first part is at most 2n plus 1 minus 2n plus 1. No, sorry, that's a 2. 2n plus 2 minus k. So it's the Young diagram of that partition is contained in that rectangle. And I'd like to tell you how I can associate to this a 0-1 word, so a sequences of zeros and ones. So what we do for this is something that's actually already exists for usual Grassmannians. This is nothing new, this O1 word. So I'm looking at my mu, but I consider it within this rectangle. And I'm going to follow, I'm going to start from this top right corner. I noticed that my hands are mirrored, so that's quite annoying. If I show the right, then you see it left. Well, yeah, sorry about that. Right, so I'm going to start from this corner here that I just indicated with something that should be looking like an arrow. And then I'm going to finish here. And I'm going to follow the boundary of my partition mu. And I'm going to record the steps that I take to get from this top right corner to this bottom left one. And if I have a vertical step, so a step south, then I record it by putting a 1. If I have a horizontal step, so a step going to the left, then I'm going to put a 0. And if I do that, in this example, I see that I get the following sequence of 1 and 0s. And now, if I look at a partition in that rectangle, for it to be a BC partition, there is an extra condition. And this is some sort of symmetry. So if I have an index, so if I have a step between the first step and the n plus first step, which is equal to the symmetric step. So I've in the example, I've indicated it with this arrow. So for instance, I see here that I have my third step there, here. And it happens to be equal to the step that is third from last here. And in that case, if I have this inequality like that, then both letters in the word must be zeros. And this is the case also for the two next ones. And I've indicated all of these with arrows. So yeah. But note that the first index here is a 1, but that's fine because the last is a 0, so they're different. So that means that I'm allowed to have that one be a 1. And the second one here is a 0, and this one is a 1. That's fine, no condition there. But here I have, what would not be allowed is if I had this one here and here I had a 1. That would not be allowed. Okay. And right, in similar way, you can define an indexing set for the odd symplectic Grassmannian starting from that one. And it has the exact opposite advantages and drawbacks compared to BKT partitions. So it is compatible with the Breuer order. So this is really useful for us. So if I have an inclusion of Schubert varieties, it translates into the reverse inclusion for the Young diagram of the corresponding partitions. However, it is no longer true that you can readily compute the codimension by just counting the number of boxes in the partition. Not in general, at least. Okay. Right, so yeah, this is a condition. So knowing if a partition is in there, it's a little bit more intricate. Maybe we need first to compute this series of zeros and 1 and check this condition. Okay. And Now, let's try and move closer to our goal of studying curve neighborhoods. There's an object called the moment graph, which will encode a lot of the data we will need to study the curve neighborhood. And that's something I'd like to explain. So this is just a graph. It is not oriented, even though the picture might look like, in the picture it might look like it is, but it is not. So the vertex set consists of all the torus fixed points. So I'm going to start talking about the moment graph of a homogeneous space. Then I look at the maximal torus in the group acting, and then I look at the fixed points for that torus action. And I have one torus fixed point for each Schubert variety. And now my edges are going to be torus stable curves. So there's, in some cases, if you have two torus fixed points, you can connect them by degree 1 or 2 torus stable curves. Sorry, degree 1 or 2 for symplectic Grassmannians. Degrees could be higher in other types. And the reason why this is interesting is that if I look at curve neighborhoods, I'm interested in curves between points in my variety, but actually with the group action, I can restrict myself to considering curves between torus fixed points. So that's why that's going to be useful. And it so happens that the moment graph for the alt-symplectic Grassmannian, so X, is just a full subgraph of the moment graph of the larger symplectic Grassmannians. So in the picture, okay, no, maybe my picture is not so, yeah, my labeling is not perfect. So the whole thing here, this is corresponds to the moment graph of the even symplectic Grassmannian. But within this, I have the part that I've highlighted in yellow, and that's, so all the vertices and edges in there correspond to the moment graph of the alt-symplectic Grassmannian. And then within this, we'll see later, no, sorry, we've already seen those two orbits Y and Z. So first of all, Z is the closed orbit. It is a subvariety of, so it's the closed orbit for both, it's a closed orbit for both actions. It's the only closed orbit for the action of the automorphism group. And this appears as a full subgraph of the moment graph of the alt-symplectic Grassmannian. And now what's very special is that the remaining vertices and the induced edges, so this, if I want, I can call that the moment graph of the open orbit. Well, so more precisely, if I look at this full subgraph of the moment graph of the alt-symplectic Grassmannian, which is induced by the torus fixed points that are in the open orbit, then it happens to be isomorphic to the moment graph of the other closed orbit. So that's really nice, because that means that actually, if I want to look at the moment graph of my alt-symplectic Grassmannian, in a way, I will always work with either of the closed orbits of the horospherical action. So I won't have to bother with spaces more complicated than these two symplectic Grassmannians. And it so happens that so Ryan and Withrow, they have this paper where they describe moment graph and curve neighborhoods in the symplectic case. So this is something that we use in this paper to understand the behavior of the alt-symplectic Grassmannian. So I'm sorry that the picture is a little bit small. Oh, okay, I've removed all the annotations apparently. But what the picture is meant to illustrate is that inside my yellow highlighted moment graph, I have to take into account mostly what's in green, so the moment graph of y, and what's in orange, the moment graph of z, and I have just a few arrows in between. And those few arrows, we are able in the paper to describe what they are, their degrees, and quite a few conditions to understand how they work. So more or less, yeah, the data about this moment graph is just the data. It's just about understanding the moment graph of those two closed orbits, which are homogeneous. Okay. So yeah. And now I'd like to go and explain how we prove the main results using this data here. So if you look at the moment graph, let me go back to it. What's relevant here is this SP2N action. But actually, for looking at the curve neighborhoods, the SP2N plus 1 action, the action of the automorphism group, of the larger group, is really what we see. And so for curve neighborhoods of Schubert varieties which intersect the open orbits, then using similar methods to that in Buch and Mihalcea's paper, we can prove that this is irreducible for any degree. And then what we do is that we compute the curve neighborhood in one specific case, because then we have the group action that enables us to get, I think that probably should be SP2N plus 1 here. Yeah, I think that probably should be that. Yeah. To get, although, no, I think it doesn't matter. Yeah. Yeah, I think that's fine. So, yeah, we compute the curve neighborhood for a specific Schubert variety. And let me, so I call it X of identity in Y. So let me explain what I mean by that, going back to the previous slide. So in this picture, maybe I'll zoom a little bit in the hope that it's a bit bigger. Yeah. So I have highlighted here two specific points. So here there is this point that I've called IDZ, which corresponds to the Schubert point in the odd symplectic Grassmannian. And here I have this point, this vertex, and that corresponds to the Schubert point in actually Y. So I said this green graph is isomorphic to the moment graph of Y, and Y is symplectic Grassmannian, so I have a Schubert point here. And so that's the thing for which it's easier to compute the curve neighborhood. So that's what we do. And I want to zoom out. Yeah. Yeah, right. So we compute in the curve neighborhood in that particular case. And then we deduce all the other cases using the action. So then
maybe I have a question. This what for variety is this special Schubert variety? Is it smooth and?
It's like.
Is it projective space or not always? I mean, it's not so important, but.
I could probably I can say which Val group element it corresponds to, but then I don't remember the criterion from the Val group element to decide if it's smooth or not. I think, yeah, it's a good question.
Okay, never.
Yeah, it's like, so for instance, here that corresponds to the Val group element, that's just the identity. And here is like 2, 3, 4, etc. up until so it's just like you shift all the entries by 1. You don't have the 1. So I don't know. It could be that it happens to correspond to. Yeah, I don't know. Sorry.
Okay. I will think about it.
Yeah. Yeah. No. That's would be nice if that's the case. Right. So now in Z. So by this I mean, what do I do if my Schubert variety is entirely contained in the closed orbit? In that case, as I said, we cannot say it's irreducible because it's not always. However, it's still going to be a union of Schubert varieties. And the goal then becomes to, well, how many irreducible components do I have? And so the way we sort that out, we look at the Schubert point, so this identity of Z, we call it, and we compute the curved neighborhood of this. And we find that there are 2 irreducible components, or sometimes it happens to just be 1. So let me explain. We find that we have a potential component that is a Schubert variety contained in Z, in the closed orbit, and we have another potential component that goes and intersects the open orbit. It sometimes happens that the part that is in the closed orbit becomes contained in the part that is in the open orbit. So in that case, what we thought what you imagine would be 2 different components happens to just be 1. But this is something we can describe. If I go back to the slides where I give the results, we have this set comp-d that describes this. I'm not going to give the combinatorial description of that set in the talk, but it's very explicit. It depends on.
And another question: these 2 components, in the case where there are 2 components, do they have the same dimension?
No. Wait, I don't think so. No.
Okay, Ryan said no.
Yeah, no. Yeah, that's.
And which is. And is the special?
No, that is a good way you can say that they are not. Is that in one case one is contained in the other? So then, yeah, in that case, sorry. In the case where it's not actually 2.
No, but I mean, in the case where it's 2.
Oh, well, it's actually 2. Yeah, then no, this still not the case. They're not. They don't have to be the same dimension.
And which one is bigger? The one in Z or the other one?
Okay. I will briefly scroll back, scroll forwards to, I think we remove, okay, I'll go back to it when I describe this.
Yeah, okay.
Because in one case we remove a partial hook, in one case we remove a hook from everything but the top row, and I need to think which one, if there's a rule, which one is bigger or not.
Okay, so maybe later I get an answer.
Yeah, sorry. Right. But okay, that's the general strategy. And what's important for some of the strategy is to have this second definition of the Kerr neighborhood, which is like the more, maybe the cleaner one. So I look at the moduli space of stable maps, in genus 0 with 2 mark points, degree D, and I look at the evaluation morphisms corresponding to either of those 2 mark points. So this moduli space, it's a little bit like just looking at degree curve on the variety, but it's, yeah, just a compactification of that. And so what I do is that I look at this evaluation morphism. So the evaluation morphism, if I have a curve and I have 2 mark points on it, then evaluation with the first mark point sends the curve to just that point, and same for the second one. And so, yeah, you can define the curve neighborhood in that way. And that's, so there's a description of these moduli spaces in the case of odd symplectic Grassmannians that's present in paper I have with Gonzalez, Perrin, and Samokin, and we make some use of that. Right. So now I'd like to explain the combinatorics. So I said in the main theorem that, well, I have, in the case where my variety intersects the open orbit non-trivially, then I have just one component. And I'd like to explain how you compute this component. And this is the formula, but the formula is maybe not the most illustrative thing. Concretely, what I do is that if I look at my partition lambda, this is an example, I've put it in the rectangle of the correct size. What this lambda O0 of D tells me to do is to remove a hook. And this is, so what I mean is that the curved neighborhood of the Schubert variety corresponding to lambda is the Schubert variety corresponding to this partition in which I've removed a full hook. Now, what happens, so that's where hopefully I can answer the question. What happens if I have something that is in the closed orbit? Well, there are potentially two components. I mean, what I've written here is still true in all cases, but it could happen that one of the varieties is contained in the other. So I'm not saying here that I always have two irreducible components. I'm saying that, yeah, I have those two Schubert varieties that intervene. And this lambda OZ of D, that one is just contained, so corresponds to a variety that's still contained in the closed orbit. And what I do is that I remove a hook like before, except I don't remove it from the first row. So yeah, that's what I've put it here in orange. Actually, I didn't really explain this. Well, I didn't explain it at all. But the top, if I have the full top row, that means that I'm contained in the closed orbit. So removing that hook like that from all the rows except the top one, that means I stay in the closed orbit. So yeah, if I compare with removing a hook, well, here, if I remove the full hook, then I would I would gain one more dimension. But of course, that could depend if my partition had different shape. So the difference between doing this and removing a full hook is like lambda 1 minus lambda 2 plus 1 boxes. And now I will try to remember that and compare with what I've removed in the other case. Okay, so this is the relatively simpler potential component. Now there's the hard bit. I'd like to describe the part that goes inside, that starts intersecting the open orbit. And for this, there's this notion of M wingtip symmetric. And the definition is really a little bit difficult, so I'm going to mostly illustrate it here. So basically, I take my partition and I follow this path, and I look at when, so here I have a horizontal step corresponding to a vertical one, here a vertical one corresponding to a horizontal one, and then etc. And that happens for 3 steps. And then I said that the partition is 3 wingtip symmetric. If I go 1 step further, then I have a horizontal step here, but also a horizontal step there. So this is not 4 wingtip symmetric. And what I do is that for the partition whose curved neighborhood I want to compute, I look at the M for which it is M wingtip symmetric, and then I'm going to remove a partial hook. And how big this hook is depends on the M here. Right. And there are two cases. So in that case, this is 4 wingtip symmetric, and I have a vertical step here. The other situation, I have a horizontal step. And what I do is that I remove, so I look at this vertical step and I just draw a barrier here in yellow. I should probably zoom here. So here, this little yellow thing is a barrier that I cannot. When I remove my hook, I need to stop at this barrier. And then for the second one, I look at the horizontal step, and this picture tells you where you put the barrier, and I do the same. I remove a hook, but I stop there. And yeah, that's how. Oops, sorry, I didn't want to do that. I wanted to zoom out, and that gives you. Oh, there's a typo here. That's not good. This is still a y of 1. It's just a different situation. Okay, and so you have those two cases, but so I remove a partial hook, and actually it is not obvious to me if that's fewer or more boxes. Okay, so let's look at this example. Here I removed 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I removed 11 boxes to compute this. If I removed a hook except for the top row, then I would remove 9 plus 3 plus 2. So I would have removed more. So yeah, actually, in that case, the other component has a larger dimension. But that's not always the case. So I think, I think it really depends. When it's not always the case that the same one has larger dimension than the other, I believe. Okay. Right. And I'm not describing when I have two components or one, but it is possible to do that. So I'll just like to, remind everyone of the theorem again. What I haven't done is describing these components, but hopefully that still gives you an idea of how explicit and easy it is to describe those components. So thanks very much.
Thank you for your talk. Are there some questions or remarks? More than that we already have. Yes, Leonardo?
So maybe I have a question. So, so for the odd symplectic Grassmannian, the fact that you had two components for gamma 1 gave two contributions in the Chevalier rule, in the quantum Chevalier rule.
Okay.
So here, the fact that you have two components in general, does it say anything about maybe other products in quantum cohomology?
That's something we haven't, I mean, maybe Ryan has looked at it on his own, but we haven't looked together at the consequences for the quantum product. So this is something, that, as I said, is a potential application, but we haven't really looked at it for now. So I don't know, maybe Ryan would be able to say more. I don't know if he has done work on that yet, but yeah, this is definitely something that could be interesting. Another potential thing to do would be to look at odd symplectic flags. There might, because they also have other potential. I mean, maybe there's a description of the moment graph like that with different parts of it.
Thank you.
I also have questions. At least, so a comment on this dimension is that at least if the dimension of the one contained in Z is bigger, then you must have two components.
Yeah, that's correct. Yeah.
So that's why I was asking someone, is it always like exactly this situation or not? But no, it doesn't matter. I can look at examples.
I think.
No. And
it's a little bit. I think you're right. This is something that could be looked at because those descriptions are reasonably explicit. But I haven't looked at it. I don't know. Yeah.
And I
if there's inclusion, then you're right. There's something. But I just wanted to tell you that in that example, the dimensions go the other way around. I seem to see that they go. So
you say this the one in Z was bigger. I see.
Yeah, I think so because.
This implies that there are two components.
Yeah, in that case there will be two components.
Yeah, but this is false.
Yeah, this implies it. Yeah, I agree. Yeah, I agree.
And so, but my question was a question is so this is probably very general. I mean, what about orospherical varieties, the other orospherical varieties? Because lots of these combinatorics, this is special to odd symplectic, the partitions, but I mean, all the geometry is very similar.
Yeah, the thing is that I would expect, at least in the ones that have the nice moduli space, so which is just one actually, then that should be fine.
Okay. So
But the others, because we still need to prove things with the moduli spaces, and some of the families are not so nice.
Maybe for lines still, you may.
Yeah, for lines that.
Okay. But for higher degrees, you have troubles because the modulus.
Yeah, there is this section of the spinor variety that should work just the same. But
Okay. Okay. Thank you.
Are there some other questions? Maybe I have some questions. So to compute the curve neighborhood, you could compute it in the bigger symplectic Grassmannian, which is homogeneous, and then intersect with the odd symplectic Grassmannian. So is there a difference?
Well, I mean, technically it could happen that the curve leaves.
Yes.
Yeah. I think that's why we don't do that. Well, yeah, I see what you mean, because we do get two components. It could happen that with intersecting, you also get two components. Yeah, I don't know. Yeah, because we do sometimes have arguments in our proofs when we where is that? Yeah, here when we look at, so in Z we have two components, one going into that starts intersecting the open orbit, and we actually have a result that it doesn't really matter when for our description when we decide in the moment graph to cross inside, to cross and go in the open orbit. So it could be that there's something like that happening as well, and that you could compute it that way. It's possible, but I wouldn't immediately know how to do it. But yeah, that's yeah. No, I'm sorry. I don't.
Okay. Thank you. Some more questions? Okay, so I don't know if we thank the speaker, but I would like to.
Yes.
And we resume in 1 hour at in France at 5 p.m.
Thank you.
Thank you.
Alright.
So, Clelia, you should also look, I think, at the minimal degrees. It's likely
No, that could be
related to this.
definitely a nice thing. Yeah, that could be interesting. Yeah, it's just, well, the paper is not short as it is, so I think that made a natural thing like that. But yeah, absolutely, that would be interesting.